thank you very much, everybody, for joining in this session. I guess we already have a very big group of people now. First of all, I would like also to express my apologies from David Groves, who was also supposed to present in this session, and unfortunately he had a last-minute emergency and he cannot connect so he will not be presenting. But in any case, we're very happy to have Julie Shortish and Tania Lopez Cantun. Julie is an assistant professor at the Department of Biological Systems Engineering at the Virginia Tech. She specializes on water resources systems. For this, she uses systems engineering methodologies such as risk analysis, data analytics, statistical modeling, and optimization tools. Tania, on the other hand, she's a PhD candidate at Carnegie Mellon University. At present, she's very interested on the intersection of climate change, urban development, data analytics, and sustainability. And well, at present, her work focuses on the aspects of long-term water infrastructure adaptation. On the aspects of long-term water infrastructure adaptation to climate change. And so, okay, that's I think probably enough from me, and I would just like to leave the floor to Julie. Julie, please feel free to start your presentation whenever you're ready.
Yeah, thank you for the introduction. Like Omar said, my name is Julie Shortridge. I'm an assistant professor at Virginia Tech in the Department of Biological Systems Engineering. And today I'll be talking about a project that actually started while I was finishing my PhD at Johns Hopkins, and then it's continued on in my work here at Virginia Tech as well. And this was a study where we were looking at the impact of methodological and modeling choices within an RDM analysis. And we used a case study in Ethiopia to do this. And so I guess to give an overview or introduction, one benefit to DMDU methodologies generally, I would argue, is their flexibility. So of course, there's the choice of which approach to use, RDM versus decision pathways versus the others. And then even within any of these methods, there's usually a decent amount of flexibility in terms of how you want to structure that analysis. And I think that's a huge benefit in terms of finding ways to make them applicable to different types of contexts. But it also means that there's a lot of methodological decisions that have to be made within any analysis. So for instance, this might be which simulation model to use, how to parameterize that. Of course, a big question is what uncertainties to include in the possible futures that you assess, and how to sample across those uncertainties. And I think in almost any DMDU type problem, there's going to be multiple objectives that are sometimes in conflict with each other. And so there's the question of how do you deal with that? And I think that anyone familiar with these methods probably kind of intuitively knows that those choices are likely to matter, and you try to make the best decision as you can. But realistically, there's rarely an opportunity to explore the impact of those choices within a given application. You know, it obviously is going to entail more time, more resources to explore the impact of those decisions that we make within this type of analysis. And so there's often not really clear guidance in terms of how to answer these questions. And so what we wanted to do with this study is to basically dive into some of those questions and assess the impact that the methodological decisions that are made within robust decision making specifically have on its analytical outcomes. And so when I talk about methodological decisions, specifically, we were looking at the statistical distributions used to generate possible futures. We were looking at how we dealt with uncertainty in our simulation model and how we dealt with the aggregation of multiple criteria. And then when I talk about the outcomes, I'm specifically referring to the analytical parts of the process. So, you know, in reality, RDM includes both analytical computational parts as well as more deliberative discussion-based components. We were really focusing on the former, the analytical parts. So specifically the scenario discovery process, where you identify the vulnerabilities for your existing or preferred system. as well as the robustness assessment, where we say, okay, which strategy or plan or design is most robust to uncertainty and climate change and other future conditions. And to do this, to look at these, we use this case study in Lake Tana, Ethiopia, which I'll discuss in the following slide. But one thing to just keep in mind with this, this project that I'll be presenting is, because we wanted to look at those methodological choices, the way that we basically did that is we applied the RDM process multiple times, changing those methodological choices, and we looked at the impact of them. And to do that, to do RDM multiple times, meant that we had to make a lot of simplifications in terms of the basic RDM analysis we did. And so, one example of that is we focused really on just water availability. Now, this is a location where there's a lot of really complex social and economic issues that should be taken into account. And I think if you were really doing RDM to decide what infrastructure to build in Lake Tana, that would be an important part of it. We did not include that, not because we don't think they're important, it's not at all the case, but just because we had to keep things fairly simple to be able to focus on these methodological questions and explore them in detail. So just keep that in mind. If you're listening and have the question of like, well, why didn't you include this particular aspect of it? That's in most cases going to be the reason. So now some discussion on Lake Tana. So Lake Tana is up in the highlands part of Ethiopia, and it is kind of a hotbed of water infrastructure development. Over the past 15 years or so, they've built a tunnel that provides hydropower, as well as 2 irrigation reservoirs. And there's an additional 4 that are in various stages of the planning process. So they're putting a lot of money into water infrastructure in this region. And generally, the objective here is reliable supply of water for both hydropower and irrigation, and of course, the economic and livelihood benefits that would hopefully accrue from that. Now, this is a place where if you look at climate model projections, there's a tremendous amount of uncertainty in terms of what the future climate is going to look like. And particularly, this is a place where if you look at future rainfall projections, the models, some of them say it will increase, share say it will go down. So you can imagine being in the position of trying to design this large scale water infrastructure for both a increase or decline in rainfall is a difficult position to be in. So, I think this is the type of problem where DMDU methods have particularly a lot of potential value. And another benefit of doing our study here is that there was already a WEEP simulation model that had been developed for the region by the International Water Management Institute, UMI. And they were kind enough to share this model with us. So that's the one that we used for our exploratory modeling. And so I guess when I start discussing some of the specific methodological issues that we started to dive into, there was basically 3 different studies that we did here. And I'm going to kind of breeze over all of them at a pretty high level, just in the interest of time. But one thing that I will mention is that all of these studies have actually been written up and published, and I'll have those citations at the end of the presentation. So there's plenty more information out there on this if people are interested in finding out those details. And of course, I'm also happy to take questions as well. But so the first question that we wanted to look into was the impact of the sampling distribution that's used to generate possible futures. And if you look back at some of the foundational literature on RDM or DMDU generally, a big motivating factor for that is that we can't say with a great deal of certainty what the probability or likelihood of different climate futures are. So we recognize that they're uncertain, but the fact remains that if you want to generate a population of samples or possible futures to run through your model, you have to use some kind of statistical method or distribution to generate those samples. And if you look in the literature and other studies, this is done in different ways. One common method you see is just selecting a range of potential values from climate model projections and then sampling across that range. So for instance, in Lake Tana, if you look at the mid-century projections, it looked like it could be anything from a decline in annual rainfall of about 270 millimeters up to an increase of about 280. So you could just sample evenly across that to generate your possible futures, and do the similar approach for other uncertain variables. But then you also see other methods, like for instance, people who use, or studies that use climate model projections directly. So you have an ensemble of GCMs, and you just take that ensemble and sample across it. Now, a lot of times what that might entail, and this was the case in Ethiopia, and I think is common in a lot of regions of the world, that distribution of changes is going to be more centrally weighted. So you're going to have more models that project changes in kind of the median range of the total model spread. And so that distribution might look more like a normal or Gaussian distribution rather than something uniformly sampled across. And so what we wanted to look at was, how does that difference impact the results that you get from RDM? And the other thing I should mention, particularly that can arise if you're using GCM projections directly, is there might be some correlation across variables. So one example of this, again, using climate change as an example, you would likely expect that some of the most extreme precipitation changes are going to be associated with the models and emission scenarios that have really extreme temperature changes. So there might be some kind of correlation or dependence between those variables. And whether or not that shows up in your possible futures, again, depends on the sampling method you use. So what we did here is we used 4 different setups for the marginal distribution of our uncertain parameters. And here we show them just for temperature and precipitation, although we did include some other uncertain parameters. And this included a uniform and a normal distribution, as well as extended versions of those. So that was basically just extending the possible futures included in our analysis out beyond what the climate models actually showed, just as kind of a stress testing or extreme case analysis. And then we also looked at 4 different setups in terms of the correlation across variables. So that included 0% correlation, completely independent, complete independence between our different variables, as well as 30, 60, and even 90% correlation. So again, even in the 90% correlation, again, I would emphasize this was just trying to see what happens in terms of the RDM outcomes. You wouldn't actually expect to see that. That's like a really extreme amount of dependence between 2 variables, but we just wanted to see how it played out in the scenario discovery and robustness assessment. And so we did that analysis and we looked at how does it impact, which of these proposed projects in Lake Tana look the most robust? How does it impact the failure scenarios that come out of the scenario discovery process? And what we found, generally speaking, was that the choice of both marginal distribution and the choice of correlation between the parameters, it really didn't have a very big impact on the robustness scores. Generally speaking, if there was a project that looked good when we had a uniformly distributed set of possible futures, that project also tended to look good under the normal distribution, tended to look good on the extended distributions, tended to look good regardless of the correlation. We didn't see a huge impact there, although that could certainly change in a different setting. Where we really saw the big impact was on the scenario discovery outcomes. So when we ran the PRIM algorithm and tried to understand what are the uncertain parameters that lead to too many water shortages, having either a normally distributed set of samples or a lot of correlation between the samples, so the types of things that could happen if you're using GCM outputs directly, it impacted both the variables, the uncertain parameters that came up as being important, and it also impacted scenario qualities, so things like the density and coverage of the scenarios that we found. And this is not a super surprising outcome if you're familiar with some of the really foundational papers on RDM and on PRIM. Some of them even say explicitly that you shouldn't be trying to do scenario discovery on a set of possible futures that looks like this slide that I've shown here. It should be, uniformly distributed across that space. But the fact of the matter is, unintentionally, this can come out depending on how you generate your possible futures. And if you do that, you're going to see impacts in terms of the scenarios that come out of it. So our recommendation from this set of the analysis was that using wide, uniform, and independent samples, that's more consistent with the later stages of the process, particularly scenario discovery, even if those samples might not be, in our opinion, the most accurate reflection of the likelihood of different climate futures. we generally don't think that the extreme ones are as likely as the more central estimates, but we can be wrong about that. But even if that's inconsistent with our beliefs, it is more consistent with the goals of the analysis, I would argue. So that was one study that particularly was led by Julia Reese, a postdoc working with me at Tech. So just to give her credit. Another study that we did using this same case study was looking at how you deal with model uncertainty within RDM. And everyone knows that there's no model out there that's perfectly accurate. And really in any context, whether it's DMDU or otherwise, there's almost always this question of how do you know when a model is good enough? And how do you know when the uncertainty within that model is potentially severe enough to cause problems? And so what we wanted to do was add that model uncertainty into the RDM process and look at how does it impact the failure scenarios that we identify, and how does it impact the choice of the most robust performance. And this was really important in Lake Tana because this was a place where we knew that certain aspects of our simulation model, there wasn't a lot of data to support them. So particularly sedimentation rates into these reservoirs are something that were fairly uncertain. We don't have good data about evaporation off of the lake itself, and so our estimates of evaporation off of these proposed reservoirs, we knew that that was a pretty rough estimate and was pretty uncertain. And even our streamflow model, there's uncertainty associated with that as well. So how we address that is we basically included coefficients that we applied to those parameters within the model, and we included those in our scenario discovery and our generation of possible futures. To just see how much of an impact they had on the results. And what we found is those model uncertainty parameters were actually a key driver of system performance. So for both of our objectives, our irrigation water reliability and our hydropower water that was delivered, both of those were largely driven by parameters related to model uncertainty. The QMOD and ETC are both model uncertainty parameters. And the way that we would explain this is that the simulation model on which a lot of this infrastructure had been planned and based was very fragile, in my opinion. And what I mean by that is that if that model was at all overly optimistic, if it was in terms of water supply, if it was underestimating evaporative losses from the reservoirs, or if it was overestimating flows into the reservoirs, then the plans for most of these planned projects, they really didn't make sense. They weren't able to meet their goals. And this was arguably a bigger impact on system performance than even climate change uncertainty. And to me, that was actually a positive finding from this because, when I was discussing this, particularly with our colleagues in Ethiopia, the way that I framed it is, there's very little that you all, or really anyone, is going to be able to do to reduce the uncertainty around future climate projections. To say for sure whether rainfall is going to go up or go down, there's really not much they can do there. But we could get a handle on evapotranspiration, I think, with some additional monitoring and studies, we could get a sense of, whether that, we could get better numbers on how much water will likely evaporate from these reservoirs. And same for sedimentation, same for streamflow generation. So to me, that was kind of a clear demonstration of how this kind of analysis can point to research priorities. What are the things that if we could find them out over the next couple of years could potentially provide a big value in terms of the design of these big, expensive infrastructure projects. And then the last study that I want to mention was looking at how you deal with multiple criteria within a project or a problem. And again, multiple objectives is kind of a key feature of most problems that have deep uncertainty. In water resources, this has obviously long been acknowledged as a key challenge. You have to provide water for different users. You have to consider environmental benefits, all kinds of different things. And so again, looking at the literature and other studies that had used the RDM approach, you see different ways that people deal with these different objectives. So sometimes you see people keep them completely separate, by saying, okay, we're going to do our our scenario discovery and our robustness assessment separately for each of our objectives. In other cases, you see them aggregated in some way using utility functions, you know, and you can use different forms of those functions, different weighting schemes to assign importance to different objectives and so forth. So you see different examples out there in the literature. And what we were interested in knowing is, you know, what's the impact of using these aggregation methods, and is there you know, an optimal way to do it, a way that has the best impact in terms of, you know, getting clear results from the RDM assessment. And so what we did, I mean, this table is showing we had 5 different individual objectives related to, and again, this is just water supply. It's not getting into, you know, social issues, which are important there. You know, there's land tenure and potentially moving people and all that. So we weren't getting into all that. Again, we were really just focusing on the, you know, water supply questions. And then we looked at different ways of combining them. So a multiplicative utility function is basically where, you know, you have to supply or meet requirements in terms of all objectives for that particular scenario to be successful. And then there's other additive ones where you could weight them equally or put priorities on specific single objectives and so forth. So we basically, you know, looked at, you know, these different methods of aggregating them, and then looked at what's the impact in terms of the scenarios and the robustness analysis. And what we found, the next slide, is, you know, generally speaking, most of the kind of common aggregation methods, you know, using some form of a utility, they led to failure scenarios that were inconsistent with the scenarios that came up when you looked at any objective individually. And more importantly than that, in my opinion, they obscured some of the relationships between system performance and the uncertain parameters that could drive it. And so an example of this is shown in this figure, where our hydropower objective, there was this clear linear relationship between change in rainfall and evaporation that, you know, would kind of cancel each other out and resulted in that diagonal line. When we had the multiplicative utility function to try to aggregate that amongst the other objectives, that relationship really washed out. And so to me, it kind of makes it so you can't see those driving factors and those connections that help us understand the system. And so, you know, generally speaking, I think if you can keep it separate, keep each metric separate, it's going to be a lot more informative. And so taking all of these studies into mind holistically, you know, I think there's a question of what kind of conclusions or best practices can you derive from them. And to me, what it all boils down to is that it's important to keep in mind the goals of a DMDU analysis. And generally speaking, those goals are to inform and to support deliberation rather than to prescribe a single solution. And so then the question becomes, what are the methodological practices that best support this goal? And we would argue from this work that using, you know, non-informative wide sampling distributions better supports that goal. You know, again, even if we think this is perhaps not the most accurate reflection of the likelihood of different outcomes, it results in a more informative outcome than if you are, you know, overly sampling the middle range of projections. Including model uncertainty, I think, is a lot of value if it can be done. And then finally, you know, I think when it can be avoided, any kind of, you know, aggregation of multiple objectives, it just kind of washes out a lot of the insights. And so if you can avoid it, that can definitely be better. And so, like I said, this has all been written up and published. So I've got the 3 most relevant papers are listed here. So you can get the details from that. And finally, I just would like to acknowledge our collaborators on this that provided, you know, models and data and just insight into the system that really supported this work, as well as funding sources. And with that, I'm happy to take questions now. I want to save them to the end. That's okay with me as well.
Great, Julie, thank you very much. It was a very interesting presentation. Very good, thank you very much. And I think we don't have questions for now. So yeah, why don't we wait till the end? And I guess for now, why don't we let the floor to Tanya? If you're ready, just feel free to jump in with your presentation, Tanya.
Good morning or good afternoon, everybody. My name is Tania Lopez Cantu, and I am a PhD candidate at Carnegie Mellon University. Um, I have been working for the past few months on this project where we're trying to apply robust decision making to increasing the resilience of major stormwater infrastructure under deep uncertainty. And just as Judy's presentation really highlighted, when we're deciding when to how to build infrastructure assets that are going to be robust to different climate scenarios, we really need to take into account all the uncertainty about future climate, which is not something that is currently done at many project level um, and infrastructure assets that are being designed and deployed today. So I really like to start most of my presentations with this slide because I think it really gives the message that whenever an engineer or an urban planner designs something and deploys something, that infrastructure asset will stay there for a very long time. And just see these two pictures, they're about 100 years apart, and the location of that drainage inlet that will convey runoff whenever it rains, whenever it rains, it's exactly the same in 1912 and in 2010. So we really have to keep in mind that whenever we take decisions about building infrastructure, these decisions will stay for long. So specifically today, what the type of infrastructure that I'm going to be talking about is stormwater infrastructure. And so most of us are familiar with this type of structures, right? They're right outside of our houses, or whenever we used to go to work by car, we would see this assets in the streets. But in any case, we have about 3 different main types of infrastructure assets, stormwater infrastructure assets that serve 2 different purposes. So we have collection assets, such as these drainage inlets that just collect all the runoff whenever it rains. We have conveyance systems, storage systems as well that like hold some amount of up to some amount of rainfall so that that water doesn't directly go into the drainage system and potentially stresses or overflows the water treatment facilities downstream. So today I'm going to be focusing on culverts, right there in the middle of the picture in the middle. So culverts are infrastructure assets that allow water or stream to flow in the natural way, and it also allows us to cross those streams, right? So these are structures. These are one of the most expensive infrastructure assets besides the storage basins, depending on how big you make them. But that we have, one that we will build for a stormwater infrastructure. So today I'm going to be focusing on these cover assets. So just a bit of background on how an engineer would go by designing one of these structures. So say you already have decided on where to build a road, and there's a stream that passes by there. So you need to do something right there, right? You have to build a culvert that allows the road to pass that stream. So that's the triangle that you see in the map. And the next thing that you have to figure out is how big are we going to make this culvert? So what is going to be the capacity of the culvert? And that's going to be a function of the volume of water that flows into that location where you're going to build the culvert. So that's the function that I have here in the left. And that volume of water depends on other variables, such as the area that contributes to this location. So in other words, the area where rainfall will fall and will accumulate, it will turn into runoff and will accumulate into different streams and will reach that cover location. So that's going to be the area that is highlighted here with the dashed line. And another very important variable to calculate this volume of water is precipitation. And precipitation comes from this type of curves that tell us different characteristics of a storm event. So, for example, how much water will a rainfall of for a storm event that maybe lasts for 2-3 hours or maybe up to a day, how much water will that storm deliver? And how frequent do we expect that storm to happen? And finally, another very important variable is this land use of the watershed. So what type of land use, what type of surfaces cover the watershed? So this is translated into the curve number, which is a number that kind of measures the relationship of when rainfall falls into the surface, how much of that will turn into runoff and different other aspects. So this map that I have here shows the land use within this specific catchment basin or watershed. And this data is taken from the National Land Cover dataset. This is specifically a snapshot from 2016. So this database classifies 30 meter by 30 meter pixels of or grids of different classes. And we have in red urban classes, and all the others, well, you can see here, like they're forest, some type of pasture, and so on. So just as I was saying before, well, infrastructure assets that we build today are going to be exposed to conditions of either climate or land use. And in fact, we have already, there is already evidence that precipitation patterns have changed across the entire United States. This map is taken from the National Climate Assessment, which shows that everywhere in the continental United States, the heavy precipitation events, so those events that are at the very the highest percentiles of the rainfall distribution for this specific period, have increased by very much, or different percentages across the country, but in the Northeast specifically 55%. And global climate models predict that these changes will continue to take place in the future. So when we think about designing something, or specifically in this case a covered, we need to take into account all these different changes that might take place in the future. And that's what I have here, right? These two different variables, not the area, but the curve number, the land use within the watershed, and precipitation might be two variables that change in the future, and we have to consider into our design. So say now that an engineer knows about these potential changes in climate and wants to incorporate some of this uncertainty into the design analysis. Here, what I'm showing is that is the historical curve that tells us the characteristics of the rainfall of a storm event, different storm events for the 24-hour duration storms, and updated this historical IDF curve, updated using some projections from downscale climate projections, from downscale climate model. So we have here that for these storm events, the amount of water that they will deliver in the future will increase. However, we have a quite large uncertainty in what could be the future, and say that now the engineer takes a decision of building or upsizing this covered using the median of this ensemble of climate models, and potentially might turn into this bigger covered. But now if we take the 75% quantile or percentile, the required capacity of this covered to be still compliant with different standards and at this specific area, providing the same level of service as it's providing today, will have to be even much bigger, right? So what this means is that even if we try to consider in some way climate change into our design, it is not straightforward what type of decisions should we take, or how big potentially we could make this covered, or what other actions should we consider to hedge this climate uncertainty, and not having to upsize the covered, but potentially do some other actions to reduce the volume of water that's going to pass by our covered. And now imagine trying to do the same analysis of how big would I make a covered, if it's, or how big would I have to make a covered in order to account for climate change in as many covereds as are owned by the Pennsylvania Department of Transportation. So they own about 10,000 covereds, and they were all built in different years, which means that they were built using different sources of information about precipitation, different sources of information about land use, and this is a case. I'm going to kind of show an animation here. Like we see a lot of blue infrastructure here, which means that they were built after 2010, and this could be good or could be bad, because we could expect that this recently built coverage will be in place for the next 70 or even longer years, and this might be actually a very much risk if the design of this coverage didn't consider any type of climate change. So this animation here is just removing the most recently built coverage, and we still have many covers that were built back in 1920, in the period between 1950 and 1970, which means that they are very old covers that might need some sort of adaptation to climate change as well. So for this, what we propose is to make a screening tool to help us prioritize which coverts might need some adaptation action. And the first component of our tool is to actually estimate what is the existing cover capacity. So this information is something that the Pennsylvania Department of Transportation doesn't readily have. They have the information that they have about these covers is their location and the size of the structure. So in this component of the tool, we back calculate what would be the maximum capacity of the covered using different engineering methods and hydraulics equations, which I'm going to show right here. So for the computation of the volume of water, or the peak discharge that flows into that into the cover location, we're using remotely sensed data and geographical information systems to estimate the peak discharge at the cover location for different types of storms. So storms that have a 100-year return period or 50-year. And if you're not familiar with this concept, it's just rainfall events that happen with very low probability anytime, any year, if you have a higher return period. So the next step is to using this information that was provided by the Pennsylvania Department of Transportation, of the size of the covers. We compute the maximum capacity of the covered, and then we compare that maximum capacity to the different peak discharges that we estimated using the different input data, so land use, precipitation, etc., to know up to which event this covert can convey. The next part of the tool is to generate many climate and land use scenarios to kind of stress test which of these coverts are going to be undersized for these different conditions, and we want to take into account climate uncertainty, and we do this by updating the historical IDF curve at each location in where the covert is built, using many or all the available downscale climate projections that are publicly available for Pennsylvania. So here is a table of the downscale climate projections that we're using in this study. There are about four, or this last one has two different resolutions, so it's actually a fifth one. But these downscale climate projections are quite different in terms of the downscaling method that was used to generate these projections. So most of the studies that we have seen in the literature use one or consider just using one for their climate assessments, impact assessments. However, just recently, we also published a study that looked at the differences between the changes in extreme rainfall between these different downscale projections for the United States. And we found that they actually have very different change signals, or they project very different change for extreme rainfall. And here I'm showing the maps for two different RCP scenarios. So the one on the left is RCP 4.5, and in the right is RCP 8.5. And for the 25-year storm, you see the maps are quite different. While some of the data sets project almost, so BCCA data set projects very mild change in the volume of water delivered by this storm. Some others project quite big change in that volume. So we are using projections from all these different four downscaled climate projections to account for uncertainty. And then we also considered two different RCP scenarios, which all these two components are used to update the historical IDF curves so that they account for future conditions. And these future IDF curves are embedded or are used as input into input to the technical to the method that we are using to compute big discharge. And then for the land use scenarios, what we are doing is we created a simple urban demand change model that populates pixels that are not at present urbanized. So they can be either any type of green, so forest or pasture. Or pasture can be like forest or grasslands. So any classes around already urban clusters that can turn into urban. That's the type of model that we're using, and we populate, or we randomly generate this change of classes up to different percentage total urban area within the watershed. So if we want to go from the watershed in the left to the right, we added at most a 5% urban area within the watershed. So finally, the last component of the tool is to estimate which coverts are going to be undersized, or potentially some of them could be oversized as well. and identify which covers are not compliant with the standards. And here I have some preliminary results of this scenario discovery analysis, where we run many simulations, but here I'm showing just for one single scenario, which is we take an ensemble median of each of the different downscaled climate projections for RCP 8.5 scenario. And for land use, we keep existing conditions. So there will be no change in land use for the rest of until the end of the century, which is highly unlikely potentially, but this is just one single scenario. And in this scenario, we find that from a total of 311 coverts, just at present, 5 of them are at risk of failing during a 100-year storm. And covers that at present are not good or can fail during this storm event increases as we as we simulate future conditions using these different downscaled projections. So for this specific input of downscale climate projections, which is from MACA, the number of covers that will potentially fail during a 100-year event, it's about 37 out of 311, and it's different other coverts for other, taking into account other data sets here. So this, out of 311 coverts that are located within this yellow area, we were able, with this tool, we were able to identify under this scenario that some of them will be at risk of failing during the 100-year storm, which can then inform priorities, and then we can have a closer look at what type of conditions are within the closer area to this cover locations where they are at risk of failing. So for example, I'm showing here a map where we have several coverts. We have 2 different coverts. This white lines are the state roads, and maybe it's not that clearly visible, but we have also some other local streets here. So for in this red cross icon here is a hospital. So what I wanted to show with this specific example is that now that we know which covers are going to be at most risk, now we can start to see, okay, is this covered which is potentially failing, is it a very important asset for the overall area where this cover is located. So if we have here the hospital and we have these two different covers, what would happen if these 2 different covers are actually at risk of failing? Do we have enough redundancy in the transportation network so that at any emergency someone is still able to arrive to this hospital? So we couldn't do this type of analysis for the 10,000 coverts that PennDOT owns, but now that we have identified a few of them that are going to be at risk under future conditions, then now we can focus on learning about the characteristics of the area and thinking about coming up with actions that then we can test whether they are robust or not using the scenario simulations that we also conduct during this tool. And with that, I have just a few remarks of this project that is still ongoing because we have completed this scenario discovery analysis, but now that we have identified some covers that are at priority, now we can continue with the steps of developing the robust decision-making approach in terms of what type of actions could we take so that we can still keep reliable those culverts. So some of the remarks from this project that we have found so far is that current infrastructure might be slightly oversized. So we didn't see the 311 culverts completely failing in the future. This means that potentially they have some added capacity coming from safety factors or traditional conservative engineering design. We saw that it is very important to take into account different downscale climate projections so that we span a large range of uncertainty for how extreme rainfall will change. And as I was mentioning before, now that we have identified some covers that will be at risk, now we can think about different combinations of structural and non-structural options to help us keep that infrastructure reliable. And finally, our tool can inform prioritization of cover assets that are most vulnerable to changes. This tool is actually very portable. The only thing that it needs is the different dimensions of the cover, and all the other open data is available for all the continental United States. So we could potentially apply the same tool for other agencies, transportation agencies. And with that, I would like to also encourage, if you're anyone in the audience, if you're doing some kind of adaptation for the United States, I would really encourage you to use the data set that we produced from this analysis where we compared the different downscale climate projections. When we did this analysis and comparing what is going to be the change, or what is the change projected in these data sets in the future, we also made available this data set of the change factors of the different storms. So if you're doing some adaptation of an asset that requires information of extreme rainfall, then I really encourage you to look at our paper and use our data. And I think with that, just want to thank all my funding sources, and I'll take any questions if there are any. Thank you so much.
Great. Thank you very much, Tanya, for your interesting presentation. There is just a question that someone posted here on the chat. So Ned Gardiner is asking us, please say more about downscaling daily data to support IDF curve development. Which downscaling methods and which GCMs are less reliable for evaluating infrequent, heavily rainfall events? Many states are interested in this problem, as well as your larger set of questions around culvert design. Is your work open source?
Yeah, so we're in the process of making this open source repository in GitHub so that everybody can also take a look at this tool. And as I said before, the change factors that we're using in this work have been already published in the literature, and they are also available for anyone to use. So I guess that answers the last question, but not which downscaling methods. Right. So the issue with which downscaling methods and which GCMs are less reliable, I would say that if you take into account only one of the data sets, which downscale GCM output, so the global climate output, to higher resolution using methods that are scientifically sounding, all of them are plausible. And if you only choose one of them, you're kind of making your decisions a little bit myopic and not taking into account all the uncertainty that there could be. So it's true that there are some GCMs that are less reliable, but I guess the point here is to look at what is the outcome of this different, taking into account all those GCMs into the analysis. What is the outcome, and is that outcome something that we really want to avoid or not?
Great, Tanya. Thank you very much. I'm not sure if there's another question for Julie as well. If not, I would like to jump in and ask a question for Julie. Well, actually, we're just on over time, so maybe we just can extend maybe some 5 more minutes the session just in case. But anyways, Julie, while you were presenting, I just can't stop wondering what was the role of local stakeholders in this process, and how did they take all these, all your findings, or in general the process that you were showing us? Could you please tell us a bit more about this, please?
Yeah, sure. So I'll answer your question, and then I also got a question in the chat that I think is kind of related and of general relevance. So I might try to answer yours and then quickly jump to the other one if that's okay.
Yeah, sure. Thank you.
Okay.
I'm sorry, I guess I missed a question in the
Oh
chat,
no, it was a private question, but it's about like communicating results and something that I think is just generally probably important and of interest. But so in terms of your question on the stakeholder engagement, so we were primarily working with the TANA sub-basin organization. So basically the interbasin organization that is tasked with managing the water supply in this region. And we mostly honestly worked with them on the front end to talk about what are your challenges in terms of doing this work, what are the aspects of this that you think are important and that we should consider, that kind of thing. But like I said, we weren't doing RDM for like TANA. Like they didn't hire us to do that. They said, well, we think this is an interesting problem. We'll happily share data and talk with you about it. But it wasn't like, a full-on application, which I think particularly people on the practitioner side who are in this meeting are more familiar with. It really was more of a, like research type focus in terms of how do you do this type of analysis. But I mean, one thing that so we would meet with them and we, share the results that we had earlier on in this project with them. One thing that came out of it, and this actually leads me directly into the question that was posed to me on the chat, like one of the biggest challenges and something that always was kind of forefront in my mind is, a lot of these results that come out of RDM, they're difficult to communicate. You're talking about pretty complex stuff, and a procedure that can be perceived as pretty complex, even for people that have an engineering background if they're not specialists in this field. So, that was part of what drove me to think about, in working with them, how do we make this understandable? And that's a lot of what, when we started talking about scenarios and things like that, it was just so much more easier to explain if we said, all right, here's what causes problems for hydropower. Here's what causes problems for irrigation, rather than trying to like talk them through a utility function that we had created. So I think there's a benefit in that sense as well. And the question that was posed to me in the chat related to that, and it was from Ned Gardner, and he had asked, I'll paraphrase because I know we're coming to the end here, about whether there were examples where aggregated metrics elucidated rather than obscured underlying patterns in the data and results and analysis. And when I think about the work I've seen that I think deals with multiple objectives in like a really impressive and sophisticated way, I mean, the main people I think of are like Joe Kapiercik and Julie Quinn. Like they've done work where there's, when they talk about multiple objectives, they're talking about performance across, dozens of different, regional water user problem where realistically you're not going to be able to do like a scenario discovery on each of those. But I think those two have developed some really interesting ways of not necessarily using aggregation to elucidate results, but to basically make this completely intractable, complex problem tractable and move forward with it. So I think that's where the aggregation can really add some value, is if if you're really talking about dozens of different objectives, then you're probably going to have to find some way to pull them together rather than looking at them all separately. But that's who I would point to in terms of doing some, interesting work where you are combining all of these, many, many different objectives.
Good, Julie.
And Ned, I hope I didn't mess up your question too much based on what you wrote in the chat.
No, it was great.
Thank you very much. It was a slightly
Thank
different
you.
question, but that was a great answer. So I can follow up with you. I appreciate it.
I'll take it.
Great, thank you very much. Well, I guess we just 5 minutes on top of our time slot. So I wouldn't like to stop you from, to the attendees to participate in other sessions. I have other questions, I guess, to you both, Tania and Julie, that I can, I guess, email you and we can discuss this privately afterwards. But in any case, it was a really interesting both presentations. Thank you very much for sharing both exciting works, really interesting tools, really interesting experiences that you have shared with us today. So again, I would like to express my first congratulations and thanks for sharing all these work with us. And well, to the rest of the audience, thank you very much for connecting. And tomorrow we will have I guess later on at afternoon times, Mexico time, we will have our third and final session on, again, mainstreaming approaches, tools and science for the water sector. So feel free and please be our guests and connect tomorrow for the third and last session. Thank you very much, everybody, for participating and connecting, and it's been an honor.